All right, this is the second video that we have for section 6.2, and in it we're going to take a look at an example of using the ability to integrate a power series in order to find the power series representation for a function. So example 2 says find a power series representation of the function f of x equals the natural log of 1 plus x and determine the interval of convergence. Now, we don't know the power series representation for natural log. However, if you take the derivative of natural log, what are we going to end up with? We're going to end up with 1 over 1 plus x, which does look like the sum of our geometric power series that we've been using. So let's write that out. So we're first going to note this. First, f prime of x is equal to 1 over 1 plus x, right? And then we can rewrite it to make it look like that sum that we're used to seeing. So we have 1 over 1 minus a negative x, which is the sum of our geometric power series, right? So we have x, well in this case negative x to the n. And that is going to converge as long as the absolute value of negative x is less than 1. Well, that implies that the absolute value of x is less than 1, which of course implies that the radius of convergence is 1, because that means x has to be between negative 1 and positive 1. So we have this power series representation, right? We know now that our derivative, f prime of x, is equal to n equals 0 to infinity negative x to n. And, you know, instead of writing it like that, why don't we pull out the negative 1? So we can write this as negative 1 to the n times x to the n. And term by term, what does that look like? Well, when n equals 0, we get negative 1 to the 0, which is a positive 1, and x to the 0 is 1, so we have 1. Then when n equals 1, we are going to end up with a minus x, and then a plus x squared, and a minus x cubed, and a plus x to the fourth, and so on. Actually, the next term is going to be minus, right, because this is alternating, so minus, and this, let's just say dot, dot, dot. Now, that is a power series representation for the derivative of f, but we don't want f, we want, we don't want f prime, we want f. So if we want to know a power series representation for f and we have f prime, how are we going to work backwards there? Well, much like in the last problem, in the last video, we needed to take the derivative. In this case, we need to go ahead and integrate what our function is. We need to integrate f prime of x with respect to x. And so let's go ahead and do that. We know that when we integrate, we end up with a constant of integration, which we usually write at the front. And then our sum is going to change using the power rule for integration. The negative 1 doesn't have an effect, the negative 1 to the n, but we know that x to the n, we need to add 1 to the power, and then we need to divide by that new power. And we know that when we do that, term by term, we're going to have that constant of integration. Antiderivative of 1 is x, and then antiderivative of x is negative x squared over 2 plus x to the third over 3 minus x to the fourth over 4 plus x to the fifth over 5 minus dot, dot, dot. And so that's our answer. We have our function is equal to a constant plus this power series. You get 1 to the n, x to the n plus 1 over n plus 1. And so there's an example of using integration, and even though we integrated, it does not change our value of r. So r was equal to 1 at the beginning, it's still equal to 1. Our interval, our radius of convergence is still 1. Okay. We're just going to find the radius of convergence here. All right. So that's going to do it for section 6.2. Let me know if you have any questions. Thank you.